Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
I'll hand over to Drew. So it's my great pleasure to be introducing Drew Purvis, who's the head of the Computational Ecology and Environmental Science Group at Microsoft Research Cambridge. Before he joined Microsoft Research, he was at Princeton, and before that he got his PhD from the University of York. So I shall hand you over to Drew.
Okay, hi everyone. Can you hear me okay? All right, well, thanks for coming to the session. I think we've seen two great examples of different stages of the process that we have to go through to try to understand and manage the planet better, which is the challenge that we're facing at the moment. So the talk we just heard showed us how we need to gather a very rich set of basic data about the environment, either now or in the past. And there's some, it's great to see that kind of really imaginative use of unusual sources like literature and so on, so that you can even go back, 3,500 years in China, which is crazy, really, but amazing. And then Yangrul's talk was a very good example of a second challenge that we face in the environmental sciences, which is that we have a lot of data that is relevant to ecological processes that govern the biosphere, but we have very little direct data on those processes. And so what Yangrul showed a very good example of is how we need to do a lot of modeling just to go from the stuff in the data, like the satellite observations, to the things that we really need, like carbon fixation and evapotranspiration. So what I wanted to focus on today, however, was another part of the process, which is saying, ultimately, managing the planet is about the future. The sustainability is about the future, and therefore we need to be able to make a large set of predictions about all different aspects of the Earth system. So, for example, how agricultural systems or forests or the oceans and so on might respond to climate change in the future under a business as usual scenario, but also use that then as a basis, use those predictions as a basis for coming up with solutions, so we can actually work out what we can do to try to create a sustainable future for all of us. So the focus of the lab that I head in Cambridge, the Microsoft Research Cambridge, so it's called the Computational Ecology and Environmental Science Group, is to try to make those kinds of predictions for various aspects of the natural world. And I've got a few of those predictions that I can show you here. I'm sorry, Yangrul, that Fetch Climate didn't work for you today. I think there was a few network issues, but what we're looking at here is a copy of Fetch Climate. The Fetch Climate itself is running on Azure, as we heard. It's one of our prototype tools. And then we're just looking at that through this web browser interface. What we're looking at there is some of our predictions for the development of the road network in the Amazon over the next 20 years. And so we've taken observations, satellite observations of roads, at more than one time period, and we've used that to build a kind of epidemiological-like model for the contagious spread of roads, and then we're able to project that forward in time. We've used a similar approach for deforestation. So here's deforestation here. And as Yangrul showed, if you hover over one of the points on the map here, you can see our predictions, which should be treated with some caution. I'll come back to that, for how the deforestation would progress this particular grid cell. Here's another prediction, because predictions aren't always just about going into the future. Predictions can be about places that we don't have very much information about. And this is our predicted map of the bird species richness across the Amazon that's been created by overlapping large numbers of polygons describing the range of different species. You can see that we predict that the bird species richness is significantly higher just south of the Amazon than it is just north. And finally, there's a prediction here of the equilibrium carbon storage. This comes from a terrestrial carbon model that we've developed in my group, particularly the work of Matthew Smith. And so we're running that model to equilibrium under the current climate, and that gives us then a map of again, our estimate, which should be treated with some caution, of course, of the potential carbon storage across the Amazon. And here's another one of our predictions that I wanted to mention too, because it also covers the Amazon, which is our postdoc Sylvia Calderaru's predictions for the phenology of the Amazon, the leaf phenology. So she built a process-based model that describes how trees allocate carbon to leaves in response to variation in light levels and soil moisture and so on, and temperature. And then that enables us to predict the leaf phenology of the Amazon into the future. Now the problem is with those sorts of predictions, however, is that the truth is it's actually relatively easy to make a prediction. I mean, you can make it verbally. I could just predict that, there seem to be plenty of people at the moment that are happy to predict that climate change isn't going to happen, or that if it does, it will be a good thing. I don't seem to have any qualms about that. Or I can, if I want, I can code up a complex model, for example, and make a prediction. But if humanity is going to actually make important decisions about how we manage the biosphere based on these sorts of predictions, then we need to be able to trust those predictions. We refer to this as defensible modeling. So we can imagine as a kind of gold standard, what would happen if you had to actually stand up in court and defend your model predictions. And so this is a picture that I found somewhere of called The Defense, and it was someone defending a model. It came up on the web somewhere, and I've added the idea of a scientist defending their model. Now, of course, this is much more than just an idea of a gold standard. It's actually starting to happen more and more. Scientists are being called in by government to justify their predictions, and in some cases, scientists have actually faced criminal charges for making misleading predictions. And this is a real challenge because to date in Earth system modeling, we've been very, very good at building interesting process-based models, and we've learned a huge amount about the world in doing that. But the truth is that a lot of the modeling at the moment doesn't quite reach this gold standard of defensibility. I'm not saying they're not defensible in a broader sense, as in people have done anything wrong exactly, but I mean in a more technical sense. Can you actually go from your prediction and go all the way backwards through all of the steps, all of the data, all of the assumptions, etc., and to justify your predictions? But I think the good news is, however, that the philosophy for how to do this kind of defensible modeling, I would argue, is now all in place. So what we're having this picture here is we start on the left with a couple of familiar ideas of hypotheses and data. And the hypotheses, in this case, are likely to be particular alternative models about how some aspects of the world works, encoded in mathematics and software. And you've heard a lot about big data. So the idea is we have data relevant to our hypotheses, and we're able to process those two things through a Bayesian inference step, what we might, in the broadest sense, call Bayesian inference. And what comes out the other side is, first and foremost, a reduced set of hypotheses, a reduced set of models. And what that means is we've learned something about the way the world works. We've been able to reject some models and accept others as good models. And so we've reduced our uncertainty in how the world works in that way. And for those models that are still in our set, we have an estimate of the parameters of those models. So as you guys know, all models have these magic constants in, alphas and betas and gammas and so on. And we're able to actually estimate those from the data, not just the best values of those, but we always have a cloud of uncertainty. We have a distribution of those parameters. And with those two things, our models and our parameters, we're then able to make predictions with uncertainty. And that's really important, because if you talk to the decision makers that need to use our models to make decisions, one of the first things they'll always ask for is some estimate of the degree of confidence that they can attach to those predictions. And this pipeline, this Bayesian pipeline, gives us a very defensible way to put those kinds of uncertainty bounds on the predictions. I just want to explain that a little bit more, because I think it's a concept that there'll be plenty of people in the room that know this already, but I'll go through very quickly. But the way I like to think of it is building through different kinds of science. So we can imagine beginning with what I would call forward modeling, which is we have some model structure, some idea about how the world works, and then we have to supply some parameters. I'm going to presume this structure is relatively complicated, so it can't be analyzed in any pure mathematical sense. It has to be simulated. And this gives us some output of some sort. And then and of course we could stop there if we like. But if we want to bring in the data, we then have the output and the data. So what do we do? So the first thing we can do is actually eyeball this, and we can, by eye, compare the output with the data. That's a perfectly rational thing to do, so I'd highly recommend doing it when you first begin building your model. And then by eye, we can decide whether we think the model output looks good against the data or not. And it's a natural step to start, if it doesn't, to start playing around with the parameters and all the model structure in order that the output looks better. And that's what I would call tuning by eye. Now this is still, probably to a large extent is the norm in a lot of areas of Earth system modeling, and that's understandable because when a model is very, very complicated, you can only go around this process so many times. That's something I'll come back to. And of course, if the model is based on a sound understanding of how the real world actually works, then you have some justification in making a few modifications and then sticking with that model, and it can be very, very useful. But if you are able to run your model more times than that, it's a very natural thing to do to replace the human eye with a computer. And if you provide a measure of fit between the data and the output, then you can ask the computer to play around with those parameters or the model structure many, many times. And that's what I would call optimization. And again, that's a great thing to do. But there is a problem with optimization, which is what's your measure of fit? What does it mean for your model to actually match reality? You can't do it by hunch anymore. By eye, you can kind of do it by eyeballing, but the computer doesn't have that kind of emotional reaction. You need to supply an explicit measure of fit. And this is a real issue, because there are often many different measures of fit, and then you're going to get a different model out at the end. But then, personally, what I find really exciting is then using a particular measure of fit called the likelihood. And this then leads to something called maximum likelihood analysis. And there are several things that are interesting about the likelihood. So one of them is it's based on very sound notions of probability. And because it's based on probability, it very naturally lends itself to concepts like, for instance, if I maximize the likelihood, then I actually have the most likely set of parameters given my model and the data. It's a slightly different intellectual space than just saying the best set of parameters to optimize my output. But it also means that I can explicitly put error bounds on parameters. Because this thing is based on probability, I can adjust parameters until, for instance, my likelihood is 5% of what it was before, kind of. I'm not going to explain that in too much detail. That's kind of the idea. And that way I can put defensible bounds on parameters. And finally, often for a well-defined problem, I would argue actually all the time for a well-defined problem, the likelihood is implied by your model and the data. There is no freedom. And that's quite nice because when you think about defending the model, you won't have to explain where your measure of fit came from because there's just the likelihood. It is what it is. And then finally, when we go to the Bayesian step, the only difference with Bayesian is the idea that we bring in some prior knowledge and belief. And the Bayesian mindset is that that's okay to do that. If you really want to get your best model of reality, you don't throw away everything you know about the world and base it purely on your data like some kind of robot. You should actually be confident about using your human brain. But it gives you a very explicit way of including that human knowledge as a prior. And the result of that is, whereas before, if you remember, we get some parameter distribution here. If the one in red is the one that you just get from the data, if you do a maximum likelihood-like analysis. And you can think of the one in blue here as the one that you believed beforehand. And what the Bayesian analysis does is it compromises between those two in the correct way. If you have lots and lots of data, you'll converge on the data one. If you have no data, you'll just go with your prior belief. And if you're kind of halfway in between, you'll end up with some compromise. So you can think of the Bayesian analysis almost being like a reasonable postdoc that does the reasonable thing given what we know and given the data. So given that pipeline is all in place, philosophically, why isn't it then that every single one of the models that we use in GCMs and agricultural productivity predictions, everything, right, hydrology models, etc., aren't simply pushed through this Bayesian pipeline so that all of our models in the environment are defensible? And there's a very easy answer to that, which is that it can be really, really hard. Sorry, that's a colleague of mine. Sorry, Matthew, I'm going to publicly ignore you. But it can be really, really hard all of these methods depend on running the model many, many times so that we can try many, many parameter combinations and many models. And as we heard earlier, some of the models we have, at least in their native state, might take months to run, even for a single parameter set. So it's quite understandable then that we have models that haven't been pushed through this pipeline. However, things are getting a lot better all of the time. So of course, we've got more computer power than we used to have. But also, there's a methodology called MCMC sampling, which is becoming more and more widespread and is becoming more and more efficient. And what's exciting about that, so the problem is that the reason you need so many runs is that for an interesting model, the size of the parameter space is huge. So if you were to do it naively, you might have to do trillions of model runs to get a decent estimate of the parameters. But what this MCMC sampling is, it's a very clever way of exploring that multidimensional parameter space. And so it very, very efficiently, wherever you start, will find the hotspot, the part of the parameter space that's the most likely, and it will then explore that by returning a set of samples from this so-called joint posterior distribution. And the other interesting thing is if you want to calculate the uncertainty on your final model predictions, it's really easy, because all you do is you choose one of these samples. So let's say you can do 30 runs, where you choose 30 of these samples at random and do an ensemble of those 30, and just calculate the distributions on whatever comes out. It's kind of magic, really. So it's still, nonetheless, it's still the case that a typical Filsback, we have our own tool called Filsback that does MCMC, but a typical MCMC run, though, for a decent-sized model might still be tens of thousands of iterations. And so, you know, if anyone fancies running a GCM tens of thousands of times just to parameterize it, let me know. But it'd be good if Azure got that fast, maybe it will. So still, at the moment, we're still going to be stuck with this trade-off between complex models that can't be parameterized in this way, but we can use simpler models that can be parameterized through this sort of defensible modeling pipeline. And just to demonstrate the Filsback, the MCMC sampling, so we have this tool called Filsback, which we use in our projects, and we've put together a little web. This is just a web tutorial type thing, just to get you familiar with the concepts. And so here you can choose a model and read about the model and look at the data and so on. But more importantly, we can actually run the sampler. And what you'll see is, this is just running in the browser in this case, because it's a small data set and a simple model. But it started out here, but this thing is, first of all, finding the hotspot in parameter space. So we're just looking at a particular plane through the parameter space there, but we could look at a different plane. So it's finding this hotspot, and then once it arrives there, it never settles down, it never freezes. It's a bit like an electron. It adopts a kind of electron orbital, and it proportions its time in proportion to the posterior density. So it's a piece of magic, really, that has appeared. It was actually invented by someone called Metropolis and someone called Hastings a long time ago, but it's come to prominence recently because it doesn't need a lot of computing power. But what's appealing about it is that it's an extremely general purpose method. So, for instance, in my group, we've used this to look at food webs in ecological systems, so that's networks of who eats what, and we specified a particular model of how we think food webs work and then parameterized that for lots of different species. We've parameterized an individual-based forest gap simulator at the scale of the eastern US and used that to simulate the biogeography of US forests and how that might respond to climate change. We've used it to simulate individual plant growth. So this is little annual plants that are growing over 90 days. We've used it to simulate the response of bird species to land use change at the scale of the whole of the tropics. We've used it to estimate the number of remaining species of plants on Earth and in each region by actually simulating the process of species discovery as a function of the number of taxonomists and the number of remaining species to be discovered and the efficiency of the taxonomist. And one of the biggest projects we've done to date is we've parameterized a new model of the global terrestrial carbon cycle. And in every case, we've thrown it through exactly the same pipeline and exactly the same tool. And in every case, we've been able to parameterize these models with uncertainty. So the terrestrial carbon model is here, and what it shows is this would be happening at every point on the globe. And carbon is coming in here. This is kind of an old school model compared to a state-of-the-art DGVM. Which are much more complicated. But of course the appeal is we were able to parameterize it against data in this way. So the carbon comes in, the carbon is fixed through the MPP, the net primary productivity, as a function of temperature and precip. That's allocated to stems, roots and leaves of plants. Those things die at a rate that depends on the climate. And then when they die, they go down into the soil, and then there's soil respiration that eventually returns that carbon back to the atmosphere, and there's fire as well. But the important thing here is that then this stock and flow model, though, each of the climate dependencies here has been explicitly parameterized against data, and what these bounds show here is the uncertainty on those functions. The yellow here being the data sets. And then because of that, we're able to make predictions for things like the equilibrium carbon storage across the world, but we're able to attach a fully defensible estimate of uncertainty on those predictions. And if we look, for example, at the relative prediction here, this is the uncertainty relative to the mean, we're able to pull out the fact that the uncertainty is much higher in, for instance, if we look at the plant carbon, is much higher at the grassland forest boundary than it is in other places. And that's because the forest grassland boundary is an area where lots of non-linearities in the model combine. And so we're also able to do things like discover the key structural uncertainties in the model, and we're able to identify the fact that of all of these different processes, the one that's the most uncertain at the moment is whole plant mortality, which hasn't got much attention in the Earth system modeling community to date. And finally, we're able to make predictions for the carbon storage of the globe out, in this case, to 2,200. We've got the mean predictions here under 3 different structural uncertainties about the way mortality works. And for each of those, we've got a 95% boundary on the predictions. So going back to this issue of complexity, I'm nearly done now, but going back to the issue of complexity then, we have to, one of the things this encourages us to do is explicitly recognize the idea of model complexity. And to illustrate that here, these are 4 different pencil sharpeners of differing levels of complexity. Starting with a pen knife here, one of the nice little sharpeners, one of the kind of desk-based ones, and then this, we call him, we have someone, Heath Robinson in Britain. What do they call him in the States? The guy that does the Rube Goldberg machine, there we go, for sharpening pencils. And so the idea here is that we know that from statistical theory, it should be the fact that there's an intermediate level of complexity which is the best for making predictions. Now we should be exploring all models because we're going to be dealing with them all in the long run for understanding and so on. But when it comes to predictions, the statistical theory is very clear, saying that it should be a model of intermediate complexity that makes the most accurate predictions. And so as we increase the complexity, if we put it through this kind of pipeline I've talked about, we should always see a better fit to the training data, but the fit to any independent test data should go up and then come back down. And there should be some optimal complexity here. And to date, we haven't really, in Earth system modeling, set out to seek that level of optimal complexity, but that's something that I think we should encourage ourselves to do. The challenge is, however, that for the more complex models that we deal with, we actually can't put them on this chart because we can't put them through this pipeline at the moment. But if e-science keeps transforming the way that it seems to be, maybe we'll obviously be able to deal with ever more complex models and find this sweet spot of optimal complexity. And of course, as our understanding increases and as we get more and more data coming through the model, we'd expect to see that optimal complexity move out through time. And then finally, I did just want to mention one thing, which is if it's come across in any way like I'm critical of highly complex models that are not very highly constrained against data, at least not explicitly, just to point out that we have built one of our own. So they are great fun to build, they're very important, and I think they do have a really important role. So this is our model of global ecosystem function, where we're actually simulating every animal on Earth. And so how they all move around and eat each other and live and die and reproduce and so on. That's called the Maddigley model at the moment. So I'm just going to have a couple of conclusions, and then Kenji, you can let me know whether there's time for me to give a 2-minute demo of distribution model or not. I don't know, because people might be interested in seeing it. But so I'd say, what we need to get to, obviously, is the point where we need to be able to collaboratively build predictive models of many different aspects of the environment at many different scales, where those models and their predictions are defensible. And I would say the philosophy is in place now. There are still some challenges, though, how to deal with the idea of a multi-component model. So it's not just one measure of complexity, but you've got different parts with different levels of complexity. And there is always this question about long-term prediction. So a lot of issues like your unknown unknowns and so on come up there. But nonetheless, by and large, the philosophy is in place. I would say the technical pieces are mostly in place, but we could definitely do with better systems for instance, specifying a model, in a more succinct way, rather than, for instance, as Fortran code. To automate the parameter estimation over large suites of alternative models. And realistically, this is still at the moment very computationally demanding. But I would argue perhaps that the single largest problem holding us back from doing this kind of work is probably sociological. That we need to really move to this idea of open modeling where we can lots of different groups can propose alternative models, and then we can compete them in a kind of spirit of healthy competition, and then keep mutating the best ones and so on, and mixing them up to give new integrated models. And of course, we'd like to see more feedback from the modeling to the data gathering, because in going through this process now, we can much more explicitly identify the key uncertainties about reality, and then that tells us what's the data that we would like to get next. And these are just a few little tips that I would encourage people, I think, and I try to remind myself of these. Like, for example, when you're doing modeling, there's a lot of pressure as an academic to come up with a high-profile PDF article that will look good on your CV, etc. But if you've built a model, can you pass it on as a model that can be used by others, as some kind of on-demand web service, or at least as a nicely commented piece of code that's open source or something. We should really try to use a heterogeneity of data and prior knowledge to build the best models. Think about the cost of complexity. Try to understand the model, not just run it. Pass on the parameters as well as the model structure. And think about this last question too, which is, how might this model actually be used by the people that are ultimately charged with trying to create a sustainable future for all of us? And shall I leave it there? Or do you think I've got time for that little demo, Kenji? Let me know. What time are we? How long? In that case, we went through a tutorial before, but we've got a couple of other tools, but I won't do those because I want to make sure we've got some discussion. So thanks.
Okay, thanks very much, Drew. I'd like to invite the other two speakers up on stage, please. And it's okay, don't worry about the chairs. We'll do it. Don't worry. So any questions for Drew, just while Yung, Rel, and Lou are coming up? Okay. Oh, yeah, great. I think the microphone's coming over to you. Okay, do you want to stand in the middle, over there next to Drew? Yeah.
Okay, Drew, thank you for a wonderful presentation. And I very much, how can I say that, agree with your whole idea about, uncertainty modeling is very important. And I'm just curious about, don't you have any plan, or haven't you tried to map the uncertainty in spatial level? I mean, can't you map uncertainty to each pixel in your whole framework?
Thanks. Yeah, so the maps I showed that come out of our terrestrial carbon model, that's right. So one thing you get is you get your mean prediction. But then that's right, you can look at the spread over those predictions as an estimate of the uncertainty. And I think there are a couple of real challenges though. So one of them is that it's important that we don't get a sort of false confidence about the uncertainty. Because there's always the problem with the models you didn't think of trying and the data sets you ignored. And so you could say subject to the idea that the truth is one of these models of mine, and subject to the idea that this is the best data, then this is the uncertainty. And so, as people talk about these unknown unknowns, this is one of the real challenges because, prediction. So if you look in different areas, so prediction in machine learning, for example, most predictions in machine learning is not about predicting into the future, certainly a long way. So it might be predicting, which ad you might click, given what you've searched for and given the information that they have about you. It's not predicting what you'll be doing in 40 years' time. But the problem is these environmental sciences challenges that we have, largely it's about predicting quite a long way into the future. And a lot could change between now and then that is not represented in the data and we hadn't even thought of at the moment. So that's one challenge. I think another is communicating different kinds of uncertainty is really hard, because there are different sorts. So variability is different to uncertainty, as you know, so there's uncertainty in the variability, and so allowing people to get a real understanding of what it of the uncertainty of your model in a way that actually enables them to make a better informed decision that includes that uncertainty is a real challenge. And in contrast to many of the challenges that we face, it's not really a challenge of maths or computing. It's a challenge of psychology and visualization and philosophy, or Bayesian philosophy. Do you guys have anything you want to add about uncertainty?
Yeah, that's a very good question. So I think the source of uncertainty is from parameters and input data and the model structure. And I believe your uncertainty is from the parameters, right? using the MCMC, then still there is another source of uncertainty from the input data and the model structure, but it is very hard to quantify. And also for the uncertainty in the parameters, it depends on how to use MCMC. There's a series of different models and they produce different estimates. So yeah, I learned uncertainty is very uncertain. Yeah, that was my conclusion. Yeah, but still I believe it is very important for the decision-making process.
Oh yeah, I still thinking, for supervised classification machine learning method, that the samples means a lot. The uncertainties of the samples that were in fact the models, and also for remote sensing images, actually the different kind of, that is different from the modeling. Yeah, but for the classifications of remote sensing images, the type of the input features, that also means a lot to the output. Yeah, that's my point.
So perhaps what I said that the philosophy was mostly in place, maybe half in place or something like that. But I definitely agree with both of those points as well. It's really, really hard, and it's and if you don't bother to think about uncertainty, I suppose it's really easy, isn't it? And as soon as you start to think about it, then kind of one thing leads to another, and you realise there's quite a lot to it. So yeah.
Any more questions from the audience? Pose a question that came in. So we're about 10 years in on the sort of e-science workshops, and the world's advanced a lot. So if you had a very large amount of compute and storage, so we have the cloud today, and I used to say to my PhD students at the start of their PhDs to think very freely. So if you had an infinite amount, say, of compute and storage, what would you do? How would this kind of improve what you're doing?
That was put us on the spot. I went first before, so one of you two has to now.
Yeah, but I think there is still a challenge because the big data does not locate in one place. Yes, even if you have very big storage, but the source of data could be scattered. For example, I am working with the NASA project, and the MODIS land product is located in the NASA Ames Center in the West Coast, and the atmospheric product is in the East Coast, NASA the Goddard Center. And they didn't allow the FedEx within their branch, so they copied from one place to the other place. It took 6 months in the NASA. So big data does not exist in a single place. That is still so. Even if we have big storage, there is still problem remains.
That's a really difficult question, actually, because I guess we must all feel like, oh, we want more computing power, but then when you actually say, we put us on the spot a bit there, Kendra, that's quite an interesting question. I think for me, I suppose, there are many things we could do if we had huge amounts of compute power. One of the things that, given my talk, it's perhaps predictable, but I think it would be really exciting to take the key, so each of the, if you look at the latest CMIP5, which is the comparison exercise for carbon model predictions, and that is just being tied up around now. I think there are something like 60 models included in that, and each of those models has several components, hydrology, the biosphere, all the rest, and so the number of possible combinations of those is huge, really huge, and then all of those have lots of parameters. And so, if I had an infinite amount of compute, maybe in principle, if I could get the data all together in one place eventually, then I could try, every possible combination of all of those components with all the parameters and somehow get the one or a few best, grand, fantastic models, maybe. It's so far removed, I think, from where we are today, but the two challenges being the raw compute, the number of runs would be huge, but also, at the moment, by and large, we can't mix and match components from different models. But if we could do all of that, then in principle, I would imagine we could get to a real step change in the defensibility of our predictions, I suppose. But it's so far out in the future. Well, I don't want to sound pessimistic, but my understanding would be that that's quite a long way out, what I've just described.
Yeah, very, very interesting questions. Actually, I think the computer power become powerful and powerful. That helped a lot. But actually, our questions still haven't been answered. That we still need more data sets, more advanced algorithms, and more powerful hardware computations to help to make new discoveries. But for me, actually I haven't used the cloud computing right now. Just like the Drew, you haven't used that Azure very much. You're relied on that can help you to get the result very quickly. But for me, I'm still doing that, all the image processing on my computer. Yeah, in one single computer. Yeah, so I hopefully, yeah, it is my hope, hopefully that will be the threshold to learning how to use the cloud computing will be much easier. So that for people who want to play around their ideas, that will be much easier for them. Yeah, that's my hope.
Very good answer.
Oh, great. We have a question there.
Oh, thank you. What can you tell me, or what experiences do you three have on interaction across models at different scales of a given situation? For instance, I'm not going to talk from the nano to the macro, but like a plant-sized model to an ecosystem-sized model. How do you deal with the interactions across these scales?
Well, that's a big topic in environmental sciences in general. I mean, it's not necessarily something you'd see lots of papers about or whatever, but if you talk to the people that think about the modeling, they'll often bring up this idea of the scaling problem, really. And I think one thing I think we can do about it is think explicitly about these transitions. So like in forest modeling, you've got the physical gas exchange processes at the scale of the stomata, then you've got multiple leaves within the canopy, and then forests are made of different trees with different species which have different leaf parameters, and then you've got environmental heterogeneity at the landscape, and somehow all of that's all within a 1 by 1 kilometer grid cell, which by the standards of most models is really fine. So you're right, there's this there'll always be all of these levels. And one thing I think that we should really bear in mind, though, is that we do have data at different scales. And I think there is a tendency for us as environmental scientists to have a sort of scale of choice. So some people prefer to think of them as a large scale, maybe stock and flow ecosystem model person, and someone more naturally thinks of themselves as a leaf level ecophysiologist. But to get what we should be doing is trying to parameterize these models against all of the different sources of data at different scales simultaneously, which has not really been done very much. So a really good example is, you can get a lot of data out of flux towers. The eddy flux towers, Younger, you'd know all about these. And so you can parameterize a lot of the vegetation model based on those short-term cycles that you can see. But some of the smaller terms that you can't see there can grow through time so that the uncertainty can become enormous in, let's say, the carbon storage after 100 years. But quite separately, we have forest inventory data sets where we actually have forest stands of different ages, up to 100 years and plus, when we can inventory the total amount of carbon. And so if we combine those two, then we can get the short-term stuff from the flux towers, but we can make sure that the long-term predictions are consistent with the chrono sequences that are coming from the inventory data. So I think there is a lot we can do to help with it. But fundamentally, it's intellectually an interesting problem as well. You guys want to comment on the scaling? Or?
Yeah, I think the scaling issue is it has long history in the biometeorology from 1960s, 1970s, John Monteith, and in 1980s, Graham Farquhar, and Paul Jarvis in 1980s. All these guys thought about how to scale up from the leaf to the canopy, not global, leaf to canopy. I think that study was done in 1980s. And then I think with the emergence of the remote sensing data in 1980s, then people started to think how to scale up from the canopy to regional to global scales, like the still running in University of Montana. And I think in diagnostic perspective, I think many work has been done, but for the prognostic perspective, it is still very challenging. Because to predict the future from the leaf to the global scale, it is very complex.
So I think I just want to thank you for the questions and thank all the speakers here and for a good discussion as well. So I think we have coffee waiting outside. So thanks everybody.